She has gone through each and every step. It's so detailed. And there's one thing that I'm pretty sure of, that if so, there's one thing that I'm pretty sure of, and it is that if this problem is given to Raksha, she can even execute it on our system. And since she has thoroughly went through this and examined each of the cases, each steps has been well considered and well done. So excellent work, Raksha. If you are here in the class, I haven't seen the participants list yet. Good work. And others, I have also received your such as Angela has sent it, and then Smriti. So let's get started with today's class. Last class we were at where were we, Rahul?
I guess slide number 29.
29. Okay. We didn't check this.
No, sir.
Okay, if it's slide number 29, then well, I don't know. I felt that it was around somewhere around this second point, deleting a subtree's topmost element. But no worries. Basically, BST in practice, I think this has already been covered. Anyone could confirm to what Rahul has just said?
Sir, we have
BST
completed all the slide
BST
number 40.
deletion, sir.
Slide, yeah. Raksha was saying something. Raksha? I
Slide
guess that
number
was Raksha.
45.
Yeah, slide number 45, exactly. So anyone else would confirm to Raksha or Rahul, so that there is these two votes.
So yeah, so exactly 45. So I wrote 29 in previous page, so I get confused. It's slide number 45. Okay.
All right, no problem at all, because your class is actually ahead in terms of what we have covered in BST. Slide 45, deleting a topmost element. So if we delete a topmost element, what we need to take care of is that, let's go through that 4 cases. There's the topmost or the root node has no children is one case. It's really basic. You just remove the link to the root and set to null. It's done. The topmost node has a right side but no left side. The topmost node has a left side but no right side. Left sides or right side sign root node ko, and then right sides or left side sign, and then the topmost node has 2 children. So basically, what we need to take care of is just that rule, which just that rule that dictates that we need to have items that are on left should be lesser in the value that are on its parent, and the right should be more in value. Okay, so these are the things that you need to take care of. Only those 2. So we'll see. Basic. It's really basic. Let me just go through it quick. The address or the link to the root node has been changed to null. That's it. And here, we discard the topmost node, but then retain the subtrees in both the cases. In both the cases, as in right subtree मात्र भएकोमा चाहिँ rootलाई discard गरेर subtree retain गरिन्छ. The address. Get me a glass of warm water, please. So the address to the root node is just changed, and it is set to the node which is, or set to this subtree, right subtree. Similarly, with the this case which has only left subtree, you can see here the before my भएको address is that of this root node line. It is changed to the address that to this address, to the left this left address, the address at the left of this node. And then So we've already talked about this. Topmost has 2 children. We also talked about this, and then we discussed on how it would be ideal to, how it would be ideal in terms of the number of steps, number of comparisons, and the storage. If we just take the leftmost element of the subtree on the right. So this one's also done, but let's see again. Left smaller items, right should have the greater items that are greater in value. So we copy the right subtrees. The right subtrees leftmost element is pig in this case. Or if pig had like a 2 leaf node which were something here around here, then it would have gone to this. It would have been chosen as the value would have been changed to its value. So copy the right subtree's leftmost element, which is PIZ, into the topmost node, which is LION. So it replaces it, and then this link, the link of on this left to the left node of this node containing the element rad is set to null. So we were here, right? And then we were here. Let's see. There's another step. So auxiliary algorithm is basically auxiliary algorithm here is to determine the leftmost node. Leftmost node चाहिँ कुन हो भनेर determine गर्नको लागि auxiliary algorithm भनिएको छ. Really basic. Let's see the animation, and then we'll be clear on it. So I'll be needing one of you to be with me here so that I'll know that you are doing good. Belina, Miss Belina.
Yes, sir.
All right. Be here and let's. So the element that needs to be deleted from this binary search tree is Fox. Is that clear?
Yes, sir.
So think of ways on how you would delete it. Think of ways on how you would delete it. If you need to delete it, what would you have to do? Please think of it, everyone. When I'm speaking to her, I'm addressing all of you as well. All right.
Hello.
Yes, Rahul. I was giving you all the time to think about the problem.
So to delete Fox, right?
Yes.
Okay, so dog in Fox place and Fox is garbage data and we can delete it.
Or you could just switch the left node address from of the node containing lion to dog. But let's see what this algorithm tells. Okay, it would be ideal. So Belina, we said parent to null, and CURR. What is the value of CURR at this moment?
Lion.
Lion. It is actually the address to the node containing the element lion. All right. So if and then step 2. What is please look at step 2.1. Is it correct? I mean, does it hold true?
No.
No. Then what happens when it goes to step 2.2?
Excuse
Is
me,
element
sir.
equal to yes?
Sir, shouldn't that dog should be at the left side?
Which one?
That fox.
Yes. Good
Sir, I think that
observation.
dog
Let me,
should be at left side.
yeah, even given this is a binary search tree, it should be on the left side. Let me edit this. I had to edit Gorilla line, Fox, rat. So E F E F E G. So let's say goat here. Okay, thank you. Nice, well observed. There was I mistake on my part. Don't know why this. Mm. So okay, so it hasn't been reflected here, and this is not Microsoft Office. So let's assume that is GOT. Really nice observation, and I'll edit this when I get hands on this Microsoft Access. Sorry, PowerPoint. So thank you. But let's for now assume that the DOG is not there and the value GOT is there. Okay. So in step 2.2, Belina, what happens in step 2.2?
So लाइन अब करेन्ट नल छैन भने त्यसको कर्सर लाइक तल जान्छ
Okay, 2.2 मा जान्छ 2.2 मा के हुन्छ what happens in 2.2 element so CURR is set to line so the value the value of LOIN is not equal to the value of ELEM which is FOX right so 2.2 pani then it comes to 2.3 and it's actually less right the value we're looking for FOX is actually less it comes to 2.2 so it's actually less so less भएपछि के हुन्छ भने less it's less right so what happens is that now parent is set to CURR parent is set to line and then CURR is set to Fox here okay and then 2.4 is not true it repeats the step 2.2 and in the second iteration it comes to step 2.2 comes to step 2 okay comes to step 2.2 in the second iteration so otherwise if ELEM is equal to CURR's element so CURR's element is Fox ELEM is equal to ELEM so now 2.2 holds true goes to 2.2.1 delete the topmost element in the subtree whose topmost node is CURR and let TL be a link to the resulting subtree. Okay. Delete the topmost element in the subtree. The topmost element in the left subtree is FOX, correct? We delete it. Whose topmost node is CURR? Already on it. Yes, that's verified. And let DL be a link. So DL is another link to the resulting subtree, which has the item GOT or dog here. Okay, it should be GOT, something that is greater, or maybe it should be in this one. It should have been a left leaf node, not a right leaf node, and that's how it's done, Rahul. Right, the least number of steps, the least of the possible storage, and the least of the time complexities. If you decrease the time complexity, if you decrease the number of the steps, the time complexity is then decreased. This is how This deletion is done here. The deletion is done here.
Sir, step 2.3 देखाउनु न
2.3. Okay.
सर अहिले हामीले 2.3 भित्र चाहिँ गरेर होइन र सर
फर्स्ट स्टेपमा 2.3 मा गऱ्यो सेकेन्ड इटरेसनमा 2.2 भित्र आएको थियो
फेरि 2.2 आयो हाम्रो
त्यसपछि 2.2 आयो कि फर्स्ट केसमा चाहिँ अब त्यो लेभल तल आउनु पर्यो नि त है
ओके सर ओके सर यहाँनिर त्यो सेट प्यारेन्ट टु करेन्ट भनेको छ नि सर
हजुर हजुर
हामीले यो प्यारेन्ट भन्ने नोडमा चाहिँ करेन्टको लिङ्क सेभ चाहिँ गर्ने होइन र
पेरेन्ट भन्ने एड्रेसमा
चाहिँ
केमा फेरि भन्नु त
प्यारेन्ट भन्नेमा चाहिँ करेन्ट चाहिँ सेभ गर्ने होइन सेट गर्ने होइन
सेट पेरेन्ट टु करेन्ट हो तर कस्तो भने पेरेन्ट भनेको चाहिँ नोड होइन ल तपाईँले अघि नोड भन्नुभएको थियो फर्स्टमा भन्दाखेरि पेरेन्ट भन्ने नोड होइन पेरेन्ट भन्ने चाहिँ तपाईँको एड्रेस मात्रै हो है एड्रेस पोइन्टर जस्तो हो ल एनीवन एल्स एनी अदर क्वेसन्स
नो सर
Okay. So what this algorithm tells you, or the algorithms that we've considered so far, is that, and also the importance of going through each of them and submitting your work in the way that Raksha did, is that you get the logic. Okay, sir, you यस्तो गर्ने हो, यो लेफ्ट को लाई डिलिट गर्ने हो, राइट को लाई डिलिट गर्ने हो, लेफ्ट को सब ट्रीलाई चाहिँ चेन्ज गरिदिने हो, यसरी भन्दाखेरि त हामीले भन्न सक्छौँ, right? We can tell it as this. यस्तो गर्ने उस्तो गर्ने भनेर भन्नलाई अलि सजिलो हुन्छ, right? But then if you see every algorithm that I have taught you, it tells you each step, right? कसरी चाहिँ यहाँ तपाईले देखिरहनु भएको छ एउटा आइटम डिलिट गर्नको लागि पेरेन्ट करेन्ट डिलिट भन्ने भेरिएबल्सहरु युज गरेर कम्प्यारिजन्सहरु गरेर स्लाइटली, राइट? सो 2.3 that's the setting of value, setting of the parent value to CURR is actually some kind of preparation for step 2.2. Would you agree or not? Because in 2.2 we are working with a lot of things here, right? So we cannot lose track of it. That is why each step ma use bhayeko variable haru pani you need to have that idea. Okay, you need to have the idea how it's being done. Kasari chai in terms of links chai kasari. So let's say that we need to delete we've already done it, but I'll again take that example. अब यो तपाईको भेरिएबल्सहरु कसरी युज भइराको हुन्छ भने लाइनको जुन लेफ्ट सब ट्री को एड्रेस छ नि, यसमा सब ट्री को चाहिँ मेन नोड को त्यो चेन्ज गर्नुपर्छ. लेट्स से फक्सलाई हटाएर डीओजी लाई चाहिँ सो हेड्स गोट. ओके, अज्युम दैट प्लिज. सो गोट यता छ र फक्स यता छ भने अब हामीले यदि फक्सलाई हटाउँदै छौं भने एड्रेस कहाँ छ त? फक्स को राइट नोड को एड्रेसलाई कपी गरेर यसमा राख्नु पर्ने हो नि त. तर हामीले के भन्छौं, सरी हटाउने अनि यसलाई चाहिँ यसमा ल्याउने. कसरी ल्याउने भन्ने कुरा चाहिँ भन्नुपर्छ कि हाउ यु डु इट, हाउ यु प्ले इन टर्म्स अफ एड्रेस, हाउ यु प्ले इन टर्म्स अफ लिंक्स. ओके, कसरी चाहिँ कुन चाहिँ कपी गर्ने हो. त्यसो भयो भने चाहिँ बल्ल एल्गोरिथम विल बी प्रिसाइज एन्ड द एल्गोरिथम विल नट गिभ यु एनी कोड राइट भए पनि त रिजल्ट त नआउन सक्छ नि. लजिकल एरर नभए अरू कुरा पनि एरर हुन सक्छ, सिन्टेक्स एरर नभए अरू कुराहरु एरर हुन सक्छ. So the point here is that you need to play with these variables. You need to make use of this address. Your address is here. Name it anything. अब यसमा चाहिँ अन्डरस्ट्यान्डिङ को लागि पेरेन्ट र CURR हामीले करेन्ट भनेर पढ्छ. त्यसरी चाहिँ that's the point, right? Everyone, I hope you are getting the message that I'm trying to convey you. So then let's move to the next slide and then So implementation. Let's not worry about the implementation. We'll worry about it after we finish the theory part. And whether a binary search tree is well balanced or ill balanced depend in the order of insertions and deletions. Or deletion can make it a well balanced binary search tree ill balanced, or a ill balanced binary search tree well balanced. Successive deletions. Let us all visualize how we will we be deleting the nodes containing the element lion, fox, and pig. All right, so let's so according to what we we just learned, both the fourth case in the cases of deletion of of the topmost node, pig lion को ठाउँमा copy गर्ने र pig लाई remove गर्ने, that would give us this one. Lion is deleted, and if we delete fox, it's the left node, but not the leftmost node. So basically this one is also done by copying the address of the left node on pig to that the address, setting that address to the address of the link of the left node in the node containing the element fox. So just that, and then the last value that you need to delete here is PIG. So PIG is a, after we come to this point, PIG is a, what is PIG? PIG is a topmost node, and we've seen how to deal with it. Please wait. This animation is going from 1 step and then 2 step back and then 3 step forward. We saw how to do this, right? And then we need to delete PIG now. We delete PIG. And copy the value of rat and then change the address. And this is something that is resultant. So yes, that's theory. So depth is only maximum depth of 2, right? So 2 minus 2 would be 0. Maximum depth minus 2 would give us a 0. So balanced and ill-balanced subtrees. And I think there is plenty messages from not in this conversation. So maybe your friends' messages. So let me check if they are having some problem. Okay. Samarpan and Prince. Okay, got your messages about your issues. So we can see how about if the depth were a lot, and if the depth were a lot, and if the deletion was concentrated to any particular branch of a subtree, all right, then any binary search tree, however well balanced, could become a ill-balanced binary search tree. So this is the point of this slide. So let's all again go to the start, because this is kind of a revision for you on the deletion of the leftmost node and the deletion of the topmost node. So please pay attention. Kune step bujhnu bhako chaina bhane we will discuss on that. Deletion of lion, fox, and pig. Okay, deletion of the nodes containing the element lion, fox, and pig. So the topmost, and then its leaf node, which, right, topmost node, the root node, its leaf node, and then the leftmost node of the right subtree. These three things has to be deleted. Deleting lion will copy PIG in place of lion, and then remove the node or remove the address to the node PIG, currently PIG, from the one that is on the left address of RAT. We set it to null, right? That is clear. Lion is deleted. Now fox. Fox is deleted. How? So this is one of the left node problem. So accordingly, link has been changed. Fox is a garbage value here, and then PIG. And then so binary tree traversal. Visit all nodes, elements of tree in some predetermined order. How do you visit them, or maybe how do you print them? How do you access? How do you access the files in a? How do you access files in a binary search tree? How do you access the elements on a binary search tree? Is the traversal of a binary search tree called as binary tree traversal. So note that it's binary tree here, right? Binary search tree. I might, binary search tree is of course a binary tree. You know that. So how do we visit the elements? So there are these three orders or three ways of traversal, which are in order, pre-order, and post-order. In order, pre-order, and post-order. So what happens is that it says in order, it says that we need to traverse the left subtree, then visit the root node, then traverse the right subtree. So let's see what it means, and then this is kind of the second last of the day. So this is basically my 2 letters of my first name, which I am keeping here. We are going to do, let's say we are going to do a post-order traversal on this tree here. On this tree here, we're going to do this post-order traversal. So post-order traversal is basically taking the left element first. And note that this is the fox here is a garbage value. We won't consider this. So Rahul, can you tell me what is the leftmost element of this tree that you see below this text editor? Leftmost.
Good.
Good. So this LRX, what this is my, I have codified it. L means left, R means right, and X means
Right.
root. Okay. So let's say that the right. So on the right there is this subtree, right? There is this subtree here. There is this subtree here, which is why I'm going to name. Yeah, this subtree. This is, see, always break it down into smaller pieces, right? You have a thulo piece. This is a subtree in itself, right? There is no one singular item. So let's break it and break it down and keep its name B. Or like B rakhu, right? This B signifies this right subtree of the topmost node or the root node that has the element lion. And what is the root node here?
Lion.
Lion. All right. Now let us consider the subtree B. Okay. In this subtree, what is, so I'll not ask Rahul. I'll ask someone else. Someone else who doesn't have a mic problem. Apeksha. Apeksha? If you have a problem with your mic, then please text here. Apeksha? Okay, sore throat. Then please message us. We will be reading your message. On this right subtree, on this right subtree that you can see here, what is the left item now? Left Makisa? Then please type fast. Apeksha, what is the left item of this subtree containing these three elements? Containing these three elements, RAT, PIG, and TIGR. Okay, so PIG, right? So PIG is the left. What is the root? What is the right one here? What is the right one here?
Tiger.
Tiger. Okay, let Apexia speak or let her send the message. What is the right one here? It's tiger. What is the root here? Apexia. What is the root here in this subtree where I'm moving the cursor? It's the root. Right, it's rat. So if we traverse this subtree, we get these three values. We get these three values. We replace it in the main one. Thank you, Apeksha. So in this post order, left, right, and root. We in this traversal we get this list here. If we have to access or print print the item. So basically, now I'll tell you how I learned it. In order, pre-order, and post-order can be pretty confusing. So I came to pre-order first. I said that the root comes first. The root has leaf nodes, so the root comes first, and that's why in pre-order, this XLR. This is my. I just coded it on the last class so that to make you understand, right? So that we have a short form or formula to understand in order, pre-order, and post-order traversal. X is for root, L and R for left and right. Note that left always comes first. Left जहिले पनि R भन्दा अघि आउँछ. And then in pre-order the root comes first. In post-order the root comes last. And then the in order is the remaining one in which the we go from left to root and right. So in this in order the root comes in the middle. This is how मैले यसरी चाहिँ याद गरेको थिएँ मैले पढ्ने बेलामा. Okay, so पछि गएर in language in computational language or grammars you might go through infix, prefix, and postfix traversal or something as such, which is kind of similar to this. Okay, let's consider this tree again, and let me call out a name. All right, Sahil. Sahil. Sahil, do you have throat problem as well? Okay, Smriti Shrestha.
Yes, sir.
Okay, so let's go on. So let's try to traverse through this tree here in order traversing. What is the leftmost element? Leftmost element.
Good.
Okay, goat. What is the root?
Lion.
And what is the right? What is the right?
Right.
So when I say right, let's pick a random alphabet.
Rat.
So right is the subtree containing the. So here right is the subtree containing the root. Rat, right?
Yes.
So pick up any random alphabet. Third alphabet bonus. Pick up any random alphabet. Anything, any word.
Yes.
Yes, okay. So if we pick up S and S signifies the subtree here, what would be in order traversal of this subtree here? यो subtree को traverse गर्दाखेरि के हुन्थ्यो in order मा? Remember, in order is left, root and right.
Pig.
Okay. Root is of this subtree.
Rat.
Right. And then the right one. Tiger.
Tiger.
Right. So then we then copy this smaller solution to the bigger solution, and then we get a in order traversal. Okay. Now, thank you, Smriti. Now we do the pre-order. This will be for the class. तपाईँहरू सबैजनाले pre-order चाहिँ do let me know the pre-order. In pre-order, root comes first. XLR. So please send this traversal. If you traverse in pre-order in this tree here, what will you get it? What will you get? Please, don't send me. Just note it down. गर्नुहोस् यो आफैले individually. Everyone, request you to do this. You have 1 minute's time.
Lion, goat, rat, pig, tiger.
No, don't call it out.
Okay,
Don't
sorry.
call it out. Okay. Okay. Srijan, Mr. Srijan. Anas got your message. Srijan. Yes. Can you send your pre-order answer to this pre-order traversal of this tree here? While Srijan types it, I would also like to request Bisal Gautam to send his traversal. Traversal ma kun kun aayo. Send that to the chat or just unmute your mic and let me know. So this is for Srijan and this is for Bisal. Yes.
Sir, excuse me,
Hazur.
sir.
Yeah. Anus. Okay, Bisal and Srijan, we don't have all the time in the day. Please send fast. I gave you a minute already to all of you.
Lion, lion, goat, pig, rat, tiger.
Okay, lion,
Goat, pig, rat, tiger.
P-I-G,
Rat,
R-T,
tiger.
tiger. Okay, thank you. Srijan, your answer. Thank you, Bisal. Lion, goat, pig, tiger. Where's rat? Is it at the last? Okay.
सर त्यो
Lion.
इन अर्डर ट्रान्सफर सर थोरै बुझाइदिनु सर इन अर्डरको
ओके यो बुझ्छौँ अनि हामीले इन अर्डर पनि बुझ्छौँ है त Okay. So pre-order is root, left, and right. So we have got two answers here, right? So let's see where one of us is confused and where one of us is not confused. So if we consider this tree here, and it has to start with root, the root here is lion. All right, and then the left is the left subtree, containing the leaf node. The topmost of that left subtree is GOT, and then the right one, the topmost of that, this subtree is rat. So let's name this entire subtree as Y.
सर
हजुर. Yes. भन्नुहोस् न, अघि पनि तपाईँले बोलाउनु भएको थियो, मैले हजुर भनेको थिएँ, फेरि तपाईँ बोल्नु भएको थिएन. Okay, so what is this Y? This Y would then be, if we consider this subtree here, we go from root, left and right. Root is rat, left is PIG, and then the right one is tiger here. Root, left and right, and then again root, left and right. So both of the answers are not accurate. Okay, Srijan and who was the other one? Vishal Gautam. The answer to this traverse is actually to this pre-order traversal is lion goat. You are correct with that, but जुन त्यो सब ट्री थियो त्यसलाई फेरि डिभाइड गरेर गर्दाखेरि चाहिँ अलिकति मिस्टेक भएको छ. सृजन आर यु अन्डरस्ट्यान्डिङ कसरी मिस्टेक भएको थियो अहिले भनेर? एन्ड विशाल?
Yes, sir.
बुझ्नुभयो कसरी इनएकुरेट भएको थियो तपाईँको आन्सर?
Yes, yes.
बुझ्नुभयो अब?
हजुर सर.
ल, थ्याङ्क यू. एन्ड सृजन? Okay, Srijan? I'm waiting while we wait for his message. Okay, let's go to in order again. कसैले in order को पनि भनिदिनुहोस् भन्नुभएको थियो. So अघि स्मृतिले भन्नुभएको थियो, right? Smriti told us and then we discussed it. So leftmost element is GOAT here. Okay, leftmost GOAT. We start with the leftmost, or maybe you can just say that यो सब ट्री छ नि, लेफ्ट सब ट्री सबैभन्दा लोवर लेभलको सबभन्दा बढी धेरै डेप्थमा भएको सब ट्री कुन छ? GOAT छ, राइट? GOAT छ, त्यसको लिफ नोडहरू छैन, राइट? सो त्यसको चाहिँ लेफ्ट, त्यसको भ्यालु हामीले लेख्यौँ लेफ्टमा भएको. ओके, सो द्याट वाज, हु वाज द्याट? वाज इट माधव और मेघान्त और अनुस? आई एम कन्फ्युज. इन अर्डर भनेर बुझाइदिनु भन्नुभएको को थियो? प्लिज अनम्युट योर माइक. So here the left thing is GOAT. If we come to the root, it's LION, and there is this right subtree which is kind of lengthy. So let's name it U. If we traverse through U, the left subtree U, the ones that contains the items rat, pig, and tiger, the leftmost of this subtree is PIG, and then the root is RAT, and then the right is tiger. Just replace it, and this is the in order traversal. ठीक sir? So Anus was wanting to say something. If you are still there, please unmute your mic. He's gone. I think it's some internet connection problem. So in order, pre-order, and post-order. Confusions, questions, doubts, reservations, more clarification required. Please unmute your mic and do let me know. Seems like there's none. Okay. So moving on to the other slides. It is just about the schematic of in order traversal. These dots. So we start गर्नु भनिएको छ. And honest class end time आइसकेको छ. भोलि हामी फेरि यसको बारेमा कुरा गर्नेछौँ. Do one thing. तपाईँको क्लास अहिले सकिन्छ. यो रेकर्डिङ चाहिँ चेक गर्नु होला है. लास्टको 10 मिनट्सको अनि बुझ्नु हुनेछ. 10 देखि 15 मिनट्सको अनि भोलि फेरि म बुझाउने छु. अब 58 भइसक्यो. सुरु नगरौँ. ओके. ल अब so the schematic for this one in order is that the root comes first and then the left comes first and then the यसरी start हुन्छ in this direction, comes up to root and then goes to the right. See, so in order traversal of a BST visits the element in ascending order भनेर भनिएको छ. So we need to prove or disprove, support or disregard this thing here. First we will construct a binary search tree. Not all, actually 3 binary search tree. You'll do it. I won't do it. It's your work. So use that visualization tool to create this binary search tree or do it by yourself. It's quicker even then. So it can be done in a binary tree or binary search tree, both this traversal. But do it for BST, because it says that in order traversal of a BST visits the element in ascending order. I've sent it to you on chat. Everyone needs to do this. Yo garnu hola. र either you prove this or disprove this. र exam in order आयो भने के हुन्छ भने, if you prove it now, if you know that it's true, then you can just write the elements in the ascending order if it's a binary search tree. If not, you'll have to traverse it then. So better now than then. So सबैजनाले यो binary search tree को यदि यो construct गर्नु 3 binary search tree when you get the time using the visualization tool or by yourself, and then do in order traversal. Check if this statement here is correct or not. Check if the statement here is correct or not. We are about at the end of our class. It's exactly 10:01. So this traversal is just what we talked about here. Binary pre post, right? So this direction here, post order direction and all of that, it says that they have a it is a basic, it is basically the schematic. Okay, post order, pre order, and in order. So post order is basically left, right, and then root. I'll be providing this slide tomorrow. Basically यो एल्गोरिदमले पनि कसरी नै गर्ने भनेर नै सिकाएको छ. We'll be starting here. Rahul will be starting here tomorrow. Slide 67. After we discuss this, if you do it, okay. I'll stop sharing now and also stop the recording since it's our end of the class.